Okay, in this video we're going to talk about subspace. And this is a concept we've seen before. We've related subspace to the concept of span, a span of vectors. Vectors span a subspace. We're going to generalize this very extremely important concept within the field of linear algebra. So here's the principal definition, and this will seem similar to what we've seen before. Suppose that V and W are two vector spaces that have the same definitions of vector addition and scalar multiplication. And suppose that W is a subset of V. Then W is a subspace of V. Okay, so a subspace is not the same as a subset. Subspace is a stronger condition. So any subspace is a subset, but not vice versa. Okay, you might have subsets that are not subspaces. Subspaces have structure because the subspace is a vector space in its own right. Okay, all right, now here's an example. Suppose we take the set of column vectors, three-dimensional column vectors, and we take the set of all three-dimensional column vectors that satisfy a homogeneous relation. Okay, so here's one particular homogeneous relation. So now the thing is, this set W, is this W a vector space in its own right? All right, so the issue now is this W a vector space in its own right? Well, let's go back and look at the definitions of vector space. Those are right here. No. Something you should notice here. We know that V is a vector space, and we know that W is contained in V. And we know that the plus and the scalar multiplication in W is the same as the plus and the scalar multiplication in V. So that means that vectors add in W the same way they add in V. Vectors are multiplied by scalars the same way they're multiplied in V. So the fact that this is true for V, the fact that vectors in V commute, that means automatically that if U and V are in W, because if U and V are in W, they're also in V. If U and V are on W, then they also commute. So this commutativity is satisfied automatically. Similarly with associativity, since V is W is a subset of V, any vectors in W are also vectors in V. So this is going to be satisfied automatically. All right, zero vector, additive inverse, that's not satisfied automatically, but associativity, distributivity of addition and scalar addition, those are all satisfied automatically. So the ones that we need to check are additive closure, scalar closure, zero vector, additive inverse, and 1. Now notice what this additive closure is saying here. What we want to show is any two vectors in W and to give a vector in W. Scalar closure says that if any vector in W multiplied by a scalar will still be in W. Zero vector means we want to show that the zero vector is in W. Additive inverse, we want to show that if U is in W, the additive inverse is in W. Okay, and we also want to show that well, actually, this is going to be true. We don't need to show this again because we know that since U is in V, it's already in W. So those are the things that we have to show: additive inverse, zero vector, scalar closure, and additive closure. Okay, so let's go back to where we are. Okay. All right, so let's see. So if we want to show additive closure, we've actually done things like this before. If we take x plus y, we get this result, and we just need to test this relationship on this result. And you can do that by using associativity, commutativity, and show that that the sum of two vectors will also satisfy a homogeneous relation if the two vectors individually satisfy a homogeneous relation. You work this out here. He's plugged in x1 plus y1, x2 plus y2, x3 plus y3 into this homogeneous relation. And then by rearranging, he shows that, in fact, this sum of vectors also satisfies the homogeneous relation. Similarly with scalar multiplication, if you take x1, x2, x3 that satisfies a homogeneous relation, and then multiply by any constant, and plug that into the same homogeneous relation. Notice the difference between this and that. The only thing is that x1 has been replaced by alpha x1, x2 replaced by alpha x2, x3 by alpha x3. This resulting alpha multiplied vector also satisfies the same homogeneous relation. Okay. If you remember, the other thing we had to show was that the 0 vector was in W. But if you go back to this homogeneous relation, the 0 vector certainly satisfies this homogeneous relation. If I put x1 equals 0, x2 equals 0, x3 equals 0, that's certainly equal to 0. So the 0 vector is in W. So the other thing we had to show was that if x was in W, its additive inverse was also in W. Now we already know what the additive inverse of any vector is, because these are vectors not just in W, but they're also column vectors. So the additive inverse has the usual additive inverse rule. We just take the negative of each component. So the question is this vector also in W? Well, check it out. Does this vector satisfy the homogeneous relation? Here's the homogeneous relation. We need to replace the x1 with minus x1, x2 with minus x2, x3 with minus x3. Does this still work? Well, it turns out it does because of the scalar multiple property. You can take out the minus. We still get 0. We're still okay. All right. So those were the important properties, and then here he mentions that the other properties are true by inheritance. For instance, commutative property, that's true because it's true for the larger set V. We don't need to check it again for W. Okay. So now we went through this example, and it turns out that we didn't have to test all 10 properties. So we want a simple, minimal way of deciding whether a subset is a subspace. We want to check as few things as possible. Okay, so here's the minimal set of things you need to check in order to guarantee that a subset of V is a subspace of V. Okay, so let V be a vector space. W is a subset of V. So W will have the same operations as V. W is a subspace if and only if only 3 conditions are met. So you only need to check 3 conditions. First, W is non-empty. Second, if x is in W and y is in W, x plus y is in, so this is additive closure. And then this one says if you multiply x by a scalar, then the scalar times x is still in W. So this is multiplicative closure. So you only need to check the 2 closure properties, and everything else will follow. Okay. All right, now if you go back to what we had to check, we also had to check on, in our previous example, we also had to check on the 0 vector. We had to check on additive inverse. There were a couple of other things we had to check as well. And let's start on this. If we have these 2 properties, can we guarantee that the 0 vector is in W? And the answer is yes, because if x is in W, then 0x is in W, and 0x is equal to the 0 vector. Okay, so if I have multiplicative closure, then I can tell that the 0 vector is also in this set in which multiplicative closure holds. Okay. Now, once you have the 0 vector in there, and then you have additive. Once you have additive closure, sorry, let me start that again. Okay, so we have that the 0 vector is in this set. What about the additive inverse? Well, we also use this scalar multiple property. If you have x is in W, then we can take minus 1 times x, that's also in W, but we know minus 1 times x is the additive inverse of x. Okay, so this scalar multiplication closure also gives us the additive inverse inside W. Okay, so if you read through this proof here, this is exactly what he's doing here. you need to show that the additive inverse is in the set, and in fact, because of scalar closure, we can multiply any vector in W by -1, and then that gives us the additive inverse of that vector. Okay. Okay. Now here I think he does this a little bit differently. He adds the vector with its additive inverse and gets the 0 vector. So that's a different way of showing that the 0 vector is in W. Okay. Okay. Now, here's an example. We can work out this example of a vector space that's unusual, that we're not used to. Consider the set of polynomials with degree at most 4. So these are polynomials of the form a0 plus a1x plus a2x squared plus a3x cubed plus a4x to the 4. So we're looking at objects that have this form. And we're going to define a subset as the set of polynomials, fourth degree polynomials, that have 2 as a root. And the question is this set of polynomials a subspace? Okay. So there are some polynomials that have 2 as a root, and there are some that don't have 2 as a root. So for instance, if you plug 2 into for x squared minus x minus 2, you get 4 minus 2 minus 2 equals 0. So yes, this polynomial does satisfy the condition, so it's in W. This polynomial, if you plug in 2, you get 2 to the 4th, 16, plus 2 to the 3rd, 8th, so that's 24 minus 7, which is certainly not 0. So this is not in W. Okay. So in order to determine whether W is a subspace of the set of polynomials, all I have to do is verify the two properties, additive closure and scalar multiplication closure. Okay. So let's try to verify additive closure. Additive closure means that if I take any two polynomials that have 2 as a root, then the question is, does their sum also have 2 as a root? Okay, so let's check this out. So P and Q are in W. That means P of 2 equals 0, Q of 2 is equal to 0. Then what about P plus Q? Well, P plus Q evaluated for x equal to 2 by the definition of addition of polynomials, that's just P of 2 plus Q of 2. That's how you find the sum polynomial. Okay, and then, but P of 2 is equal to 0 because 2 is a root of P and 2 is a root of Q, so we get 0. So yes, the sum of two polynomials that have 2 as a root also has 2 as a root. Scalar multiplication is similar. Suppose I have a polynomial P that has 2 as a root. If I multiply that by any constant, and I evaluate that new polynomial at 2, well, this is the definition of scalar multiplication of a polynomial. To get the result, I just multiply the result by 2. But the result of P of 2 is 0, so I have alpha times 0 is equal to 0. So we do have that polynomials that have 2 as a root form a subspace. In this case, we're only looking at polynomials of degree 4. Okay, so this gives us a way of simply finding new subspaces. Okay, now there are examples of something that's not a subspace. Here's a subset that's not a subspace. Okay, so for example, if we take the set of vectors in C2, set of two-dimensional vectors, such that this inhomogeneous relation is satisfied. Now the question is, the set of all vectors that satisfy this inhomogeneous relation, is this a subspace? And the answer, quite quickly you can find, is no, because the 0 vector is not in this set. 0, 0 does not satisfy this condition, because we'd have 0 plus 0 is equal to 12, so that's not, so 0, 0 is not in the set. Usually that's the first thing you try if you want to check whether something is a subspace. Now here's another one. Let's look at the subset of C2 such that the product of the two entries is 0. Now, is 0, 0 in this set? Actually, yes. Okay, but let's see, do we get additive closure? Like, try something else. Okay, so take 1, 0 plus 0, 1. The sum of that's 1, 1, but 1, 1 is not in the set because it's not true that 1 times 1 is equal to 0. So additive closure fails. This is not a subset of the two-dimensional vectors. Okay, here's another example of a subspace where subset that's not a subspace. If we take all vectors that have integer entries, well, the 0 vector's in there, and this is actually closed under addition, but if you multiply by any fractional scalar, it's no longer in the set. For instance, if I take the vector 2, 3 and multiply by 1/2, I'm going to get 1 3/2, but this 3/2 is not an integer, and we're only looking at the set of vectors which have integer components. Okay, there's some examples of subspaces that are trivial. A vector space is a subspace of itself, and the 0 vector is also always a subspace. But these are not very interesting. Okay, so let's go to something more interesting, something that we've seen before. We've talked about the null space of a matrix. Remember, the null space of a matrix is X such that AX is equal to 0. So the null space of a matrix is not a space of matrices, it's a space of vectors. Okay? And if A is a m by n matrix, A has m rows, n columns. So that means that X must be in Cn. The number of rows in X must be equal to the number of columns in A, because that's required for the matrix multiplication. Okay, so here we have a formulation of a null space of A. Okay, and the question is this null space actually a subspace of Cn? And you can directly verify this. I think that we've actually verified things very much like this. You only need to check two things. You need to check that this null space is closed under vector addition, and it's closed under scalar multiplication. Okay, so to prove that it's closed under vector addition, you want to suppose that both x is in the null space and y is in the null space, and establish that x plus y is also in the null space. And that means that the null space is closed under vector addition. Okay? So what does it mean that x is in the null space? It means that ax is equal to 0. Does it mean that y is in the null space? That means ay is equal to 0. What do we want to show? We want to show that x plus y is in the null space. So let's check that a times x plus y is equal to 0. So let's start out with a times x plus y. Well, we can do this distributivity of matrix multiplication and break this up into ax plus ay. We've seen this before. But ax is equal to 0 because we have that as a hypothesis, and ay is equal to 0 because we have that as a hypothesis. And 0 plus 0 is 0. So in fact, x plus y is also in the null space. X plus y also satisfies a times x plus y is equal to 0. Okay? Now we have to do the same thing for multiplicative closure. So that means that we should suppose that x is in the null space and show that any scalar multiple times x is also in the null space. Okay? So we're supposing x is in the null space, which is the same thing as supposing that ax is equal to 0. And we want to show that ax is also in the null space. So we want to show that the matrix big A times ax is also equal to 0. Let's do it. Big A times the matrix ax. Well, this is also a property of matrix multiplication, that we can pull out the scalar multiple. We already know that ax is equal to 0, and any scalar multiple times 0 is equal to 0. So we've shown that the matrix A times scalar ax is also equal to 0. So ax is also in the null space. Okay, so the null space is in fact a vector space. Is in fact a subspace. Okay. Now, let's go a little bit farther, kind of combine the two examples that we have. The first example was showing that we can write the set of vectors that satisfy a linear homogeneous relation. No, not this one, sorry, this one here. The set of vectors that satisfy, whoops, where did it go? Let me find it just a second. Here it is. In this example, SC3, we showed that the set of vectors that satisfy a linear homogeneous relation is actually a subspace. So let's go back down here. Suppose we have a bunch of linear homogeneous relations. Okay? Not just one, but several. So the question is this set of vectors also a subspace? Well, you could apply the same proof relation by relation, but there's an easier way. In fact, this set of linear homogeneous relations can be expressed as in terms of a matrix, and the solutions can be expressed as the null space of a matrix. Okay, how do I get the matrix? Well, I just take the matrix of coefficients of this system of equations here. Okay, here's my x1 column, x2 column, x3 column, x4 column, x5 column, and you just pull off the coefficients. For instance, the first row here, 3x1, so this is a 3, plus 1x2, so this is a 1, minus 5x3, so this is a minus 5, plus 7x4, this is a 7, plus 1x5, this is a 1. And you did the same thing for all of these rows. So this set of linear homogeneous relations can be expressed as the same thing as the null space of A. Okay, so we're kind of tying some things together. We're showing, in fact, that when we talked about null space, this null space is a vector space in the sense that we have defined. So we're